Okay, so we want to look at this problem that we have. Calculate dy by x if y is equal to tan to the power x with the aid of logarithms. So in other words, that is what we call a logarithmic differentiation, where we take advantage of natural logarithms to help us to differentiate. So now if we have y is equal to tan x to the power x, when we uh, take advantage of natural logarithms, you can see that when you have y is equal to tan to the power x, this is actually an equation. So whatever you do on the left, you also do on the right, just as you have learned in your early classes of learning. So that means if I apply natural logarithms on the left-hand side, I must also apply on the right-hand side. So that means if I apply natural logarithms ln, y would be equal to the ln of tan x to the power x, like that. And once we have done this, then I can take advantage of the laws of logarithms, and the law which says that if you have ln a to the power b, this is the same as b ln a. So that's a law of logarithm that I can take advantage of now. And if I apply that law, that means I can have this here as ln y is equal to x ln tan x, x ln tan x, like that. So x times ln of tan x. Now, at this point, you can see that this equation that I have here is what we call an implicit function, which we must differentiate implicitly. Now, when we differentiate implicitly, we differentiate term by term. So we differentiate ln y, and when you differentiate ln y implicitly, this is what we get. You get 1 over y dy by dx, and you come to the right-hand side here, you see that now what I have here is a product. So I'm going to use the product rule to differentiate the right-hand side. Remember, with the product rule, if you have, say, y is equal to u times v, when you differentiate using the product, this would be equal to u times the derivative of v plus the derivative of u times v. That's the formula that we use to differentiate product. So now, if I differentiate this according to this formula, I'm going to get here x times the derivative of ln tan x. So it's the ln of tan x. When you differentiate the ln of tan x, what you get is sec squared x over tan x. And this comes from the simple law which says that if you have y is equal to ln f of x, when you differentiate that, what you get is f prime of x over f of x. That's exactly what we have used here. So now we have differentiated ln tan x plus. Now I differentiate u, which if I differentiate x, I get 1. So this would be 1. So this would be plus 1 times ln tan x. 1 plus ln tan x. Now that's what I have. Now remember, we are being asked to calculate dy by x there, right? So ultimately, if I'm to write this a little bit neatly, this is 1 over y dy by x is equal to, I can write this here is now x sec squared x over tan x plus ln tan x, like that. Now remember, I want to calculate dy by x. So what do? I can see on my left-hand side, I have 1 over y. So I can multiply both sides by y. Multiply by y both sides. So this y here and that y cancels. And what's left on the left-hand side, just dy by the x. So dy by the x is given by y into x sec squared x over tan x and of course plus here the ln of tan x, like that. And recall in the final solution here that y is actually the same thing as tan x to the power x. So I can replace this y with tan x to the power x. So this becomes tan x to the power x into x sec squared x over tan x plus the ln of tan x, like that. So this becomes my final solution, which is the derivative dy by x of this particular function. So we have differentiated this function by taking advantage of natural logarithms. In other words, that's what we call logarithmic differentiation. So you find that as you are dealing with logarithmic differentiation, you must have prior knowledge of implicit differentiation. So yes, that's how we differentiate this function.